Welcome back, guys, to another video. In this lesson, we are going to cover more in depth the collision theory and also how to calculate the change in enthalpy of reactions. So just as a quick recap, in collision theory, we stated that atoms, ions, molecules, they have to collide. They have to do so in the proper orientation, and they must do so with the right amount of energy. And all of this is to produce a chemical reaction. So whenever those bonds are being broken and formed, we have the understanding that energy is required. So today we're going to pretty much figure out how much energy is required and how we determine that. So before we move on to that, however, we are going to talk about catalysts because this kind of throws everything that we've talked about so far out of the window. So what a catalyst is one of those factors of reaction that we learned in our previous lesson, where we stated that there are things that we can do to kind of help speed up the process of reactions, and one of them is a catalyst. Now, what a catalyst is really is that it helps in the orientation of the reactants. So even though some of the particles and the molecules that we talk about will collide and randomly will happen to collide in the correct orientation, every single time for those collisions, there's going to be energy that is needed. So whenever we have a catalyst, what it does is that it helps the reactants interact in the proper way. So it pretty much figures out a way of fixing the orientation. So instead of relying on random collisions that happen to have the right orientation with enough energy, what a catalyst does is that it ensures or it assists that the orientation of those reactants is in the proper way, so at the proper angle. So therefore, we are not just relying on random collisions, we're helping them. And also, because we're not just relying on those random collisions, we are not utilizing as much energy as otherwise we would need. So catalysts help us in decreasing the activation energy. So if we look at a graph such as the one shown here, we have the catalyst energy curve being shown in black, and then the regular one in red. So you guys can see here that once we have the the enzyme or the catalyst, we would have a decrease in the activation energy. And again, that goes back to the idea that we don't need it because the catalyst helps ensure that the orientation is correct. So just so that you guys know, the curves usually will have to be lower than the regular one that we would normally draw. And that signifies that there's a catalyst being added. Just as a, again, recap, endothermic, we have a change in enthalpy that is positive, and exothermic, a change in enthalpy that is negative. So whenever we talk about the products, we want to always subtract that from the reactants. All right, so let's talk about how then can we determine what is that change of enthalpy, because in some of the examples that we've seen in class, we have been given the value for the reactant and the product. Well, that's not always going to be the case. Sometimes we are given the reaction and we are going to have to figure that out ourselves. Now, we haven't quite talked about heat of formation, but as a very quick thing, it's this symbol right here on the table right on the bottom left side of the screen. It's delta HF. And what that signifies, it's the heat of formation that tells us that is how much energy is required to produce or to break the particular bond in that compound. So for example, we have carbon dioxide, and it's telling us that it has a negative 393.5 kilojoules per mole. So that is how much energy would be required to create or to form the bonds that are utilized in a compound for carbon dioxide. So it's a very simple idea here, but it's a very powerful concept overall. So all we're doing, just like we did before when we were looking at the energy diagrams, all we have to do is the products, the total energy to form the products minus the total energy of the reactants. So first we have to figure out, okay, well, what's the total for the products and what's the total of the reactants? Because that would give us our change in enthalpy. And remember, just like I showed you guys in the previous slide, if the change in enthalpy is positive, then we have an endothermic process. If it is negative, then we have an exothermic process. So let's look at the values here. We are told that we have carbonic acid, and we're told that it's formed when carbon dioxide in the environment mixes with the water in the following reaction. And we have the reaction shown here on screen. Just like before, we always want to make sure that the reactions are balanced. We'll see in the next example what the coefficients would what the effect of the coefficients would be. So in this question, we're being asked to calculate the delta H for the formation of carbonic acid and state whether the reaction is endothermic or exothermic. So here we're looking at two different answers, right? What's the delta H, and also is this endothermic or exothermic? So let's do this. First, figure out how much is the total for your reactants and what is your total for the products. So for carbon dioxide, we have negative 393.5. And since there's only one mole of the carbon dioxide, we only add it once. Then we will take that and we would add it to the heat of formation for water. We are told that that is negative 241.8. And also there's only 1 mole of the water, so we only add it once. So then we would need to have our information for carbonic acid. And what that would be is also shown here on screen. We have our value for that one, which is negative 275.2. Now, of course, because we want to know the total of the reactants and the total of the products and then subtract those from each other, we would have to take our calculator, right? And I'm not going to make the little screen I usually show you guys here because these are just simple additions of negative numbers. So that would be negative 393.5 plus, right, a negative 241.8. And of course, because we are adding negatives, we would expect this number to be an even bigger negative number. So we come out to be an answer of negative 635.3. But that is obviously not our last final answer because we are being asked for the change in the delta. So we would have to do products minus the reactants. So the product is negative 275.2 minus negative 635.3. And as you guys know, subtracting a negative, I'm sorry guys, subtracting a negative would end up being like adding it, right? So when we have negative 275.2 minus negative 635.3, we end up with an answer of 360.1. And that would be kilojoules per mole. So this right here is our answer for delta H. And because this answer came out to be positive, right, 360.1, then we know that this entire reaction is endothermic. All right, let's look at one more example. So this is the one that I was telling you guys that it is important to make sure that our equations are balanced. Just for the sake of time on the video, I balanced this one, but don't expect the reactions to always be balanced when they're provided to you on examples. So we are told that the combustion of acetylene is the reaction that occurs in torches used in the welding industry. The following reaction shows the combustion of the products and the carbon dioxide and the water. So we have our entire reaction here balanced already. We are being asked the same two questions. We want to know what is the delta H for the combustion and also state if the reaction is endothermic or exothermic. So I'm a very visual person, so I like to just always break my reactions in half because sometimes the numbers can become a little confusing. And we just start. We need to know what is the value for the products. We want to know what is the value for the reactants because we need to subtract them. We want to know that difference. We want to know how much energy was used in the entire process. So we are going to find, and guys, these are standard numbers. I have them here on the screen, but honestly, you could just go online and look them up. And what we're going to do here is going to be the first one, which is 227.0. And notice how we have a coefficient of 2. Because we have a coefficient of 2, that means that we need to multiply this value by 2. There's many ways that you can write this down. I personally like to just multiply them inside of the parentheses, but you could also do it outside and factor it in. It's completely up to y'all how you want to do this. Just make sure you account for it twice because it has a coefficient of 2, right here in front. Then we have a total of 5 oxygens. Now, here's a great time to think about what the numbers that we're writing down represent. Because it's called heat of formation, meaning that is how much energy is utilized to make the bonds that create a compound, right? So if you think about it, when we talk about an element such as oxygen, and it's just an element, right? It doesn't have any particular bonds that is forming with other elements to form a compound. So because it is an element, its heat of formation would be 0 because it does not take energy to form the oxygens themselves. They are elements. If they were to bond with other elements, then we would need energy to make those bonds and to break them eventually. So you might be thinking, well, there's 2 oxygens, right? Well, yes, there is 2 because oxygen is a diatomic. So those are ideas that we cannot forget. These are going to continue to come over and over in your chemistry classes. So those are important ideas. Don't forget them. So because oxygen is an element, even though it's a diatomic and it has a 2, and there's 5 moles of it, it still has a heat of formation of 0. So that's why I wrote a 0 in. And regardless, right here at the bottom, I also put in 0. So basically any element, so again, any element, even if it's a diatomic, is going to have a heat of formation of 0. That's something that you will be expected to know. All right, so let's move on. Then we have 4 carbon dioxide. So we're going to do 4, right, times the value for carbon dioxide, which is negative 393.5. And then we're going to add that to the value for water, but there's 2 of them, right? So we're going to do 2 times negative 241.8. And then we're going to take our calculator and make sure that we know the total for the reactants and the total for the products. So we are going to have for our reactants a total of 454. And our products, I'm going to have to get my calculator and do all of that because as much as I wish I could do all of these in my head, sadly, I am not one of those people who can. I would at least have to think about it for a little while. Okay, so then our answer for the products is going to be negative 2,057.6. So because we want to know the change in enthalpy, we are going to have to do negative 2,057.6 minus 454. And because that is a positive number, right, subtracting would then give us an even larger negative number. So we would end up with the answer of negative 2,511.6 kilojoules per mole. And because our answer came out to be negative, we know then that this is an exothermic reaction. All right, guys, what I'm going to do next is going to give you another example here by yourselves. And what I want you guys to do is just pause the video, work on it by yourselves, and then I'm probably going to wait like 10 seconds, and then I'll post what the final answer is here. What we are going to do in our next lesson is going to start looking and make a transition into the heating and cooling curves and how the heat of formation and the different phase changes have to do with what we're learning right now, which is trying to figure out just how much energy is utilized to break bonds and form new bonds. Thank you guys so much for watching, and just wait for another couple of seconds so you can see the final answer for this last question. Thank you.